So since we'll be working with drivers longitude and latitudes, we need to extend our DB to support this geospatial data. Even though MySQL and Postgres do support them, we need to discuss how does that work. We can maintain indexes on latitude and longitudes. Now, to find all nearby drivers of passengers' location, say XY coordinates, and if we're searching in a radius of say D, we can query TB like select all from driver location where latitude between x minus t and x plus t and longitude between y minus t and y plus t. Now we have just oversimplified this query here, which is fine, but problems is when we receive the lists for longitude and latitude ranges. We'll need to find their intersections, which could be really inefficient for our servers. Also, since each user's location will be different, we can't simply cache it and return the result from cache. So, is there a way to reduce the list size of drivers? One way to solve this is using a technique called geospatial indexing. It often comes handy in various system designs. What we do in this is we divide the whole map into smaller grids like this. Each grid is defined by specific ranges of longitude and latitude, and each grid will store the driver's locations who are inside it. Now, how it helps us is we don't need to perform the intersection operation. Suppose that a user is at this point, we only need to find his neighboring grids and query just these grids to get all the drivers inside it. For the time being, we can define these grids as static, that is, they don't change at all. Let's say each grid is 10 mile long. So we can easily find the grid number if we are given a location in longitude and latitude and its neighboring grids. So we'll need to store the grid ID also, maybe let's say a 4-byte number to uniquely identify each grid. Let the grid ID 0 be user's own grid and grid ID 1, 2 until grid ID 8 are the user's 8 neighboring grids. So we can extend our query with additional grid ID filter. We say grid ID in grid ID 0 to grid ID 8. So in this way we are massively improving the runtime of our query. Now let's think if there's a way we can improve this even further. Since our grid IDs are limited, we can store a hash table for indexing this where the key of hash table is grid ID and the value is the list of drivers in that grid ID. Now this is a good approach, but earlier we assumed that grids are static. So what if some grids have much more drivers than the others? We can call these grids as hotspots. Suppose something like Delhi will be filled with drivers, so we will return a lot of results there. But something like Pacific Ocean will have drivers only on the coastal sites. And in rural areas, there may not be any drivers at all. So to solve this, what we can do is adjust our grid size such that whenever we find a grid with lots of drivers, we can break it down to create smaller grids and keep doing this recursively. For example, let's say we don't want to have more than 500 drivers in a grid. So we can have faster searching. So whenever a grid reaches the limit, we break it down into 4 grids of equal size and distribute drivers to them and keep doing this recursively. This means that heavily populated areas like Chicago will have a lot smaller grids, whereas sparsely populated areas like Pacific Ocean will have large grids. So what data structure can we use to store this information and create grids dynamically? Since we need an area to reference 4 sub-areas, this could be solved by a parent-child dependency data structure like perhaps a tree or a graph. Let's say each node of our tree can have 4 children representing a grid. If a node reaches its limit, we will break it down to 4 more children, which means that only the leaf nodes will keep a list of places with them. Let's call this tree a git tree. The root node will represent the whole world in one grid. Since it will have more than 500 drivers, it will break down and this will keep repeating. Now how do we find the neighboring grids in this case, since we don't have a fixed sized grid like we had earlier? So first we will need to find the user's grid, so we will start from the top. And based on the user's location, we traverse the grid until the leaf node. If the user's grid has enough drivers, then we can just return that grid. But if not, then we need to find its neighboring grids. We can do this by simply keeping a parent pointer on each node and traverse up to find the neighboring grids until we have enough drivers to send write requests to. Once we have all the grids, we can easily query the database to find all the available drivers within these grids. We can even choose to store all the driver IDs in the leaf grids itself, rather than maintaining another column in driver location table. Now, when a new driver is registered, we can traverse the grid tree and store his ID in the corresponding grid to his location. Now, one problem that we see here is as the app grows, there will be more and more drivers which may not be able to fit in a single server, or a single server may not be able to serve all the traffic. So, that's our clue to think on the lines of sharding. So one way to decide a shard key could be the zip codes, but the problem will be some areas could have become hotspots. So another way could be using a hash function to map each driver ID to a shard where we store the driver. While building the grid tree, we iterate all the drivers and calculate the hash of each driver ID to find the server to store data to. To find drivers near a location, we'll have to query all servers and a centralized server can aggregate these results. We can further use consistent hashing on this to have as much equal number of drivers in a shard as possible. This means that each shard could have different structures of grid tree. Now we can also optimize this to use master replica approach so that our main database is used only for writing data and replicas are used for all the read operations. There could be some seconds of replication lag, but for our use case it's fine. We can also have a secondary replica in case primary goes down. In case the secondary also dies, then we may need to rebuild the grid tree from scratch. The brute force way to do that would be iterating through the database, but this would be quite slow and inefficient. A better way may be to use a reverse index that will map drivers to their grid tree server. We can have a separate grid tree index server that can hold this info. The key could be grid tree server and the value will be set of all the drivers. Once again, we can use a secondary replica in case primary goes down, and if the primary goes down, we can rebuild the grid tree from scratch, iterating the DB as last resort. We can take advantage of cache in previous parts of our application, such as while retrieving drivers from hot places. LIU scheme would be fine for our use case. For load balancing, we can use it at two places, between clients and app servers, and between app servers and backend server. A round robin would fit fine for our purpose. Now we also need to support how to update the grid tree since the drivers will be reporting their locations every 3 seconds. We can simply search for the driver's grid and if his new position is in another grid, we can remove him from current grid and add it to the new one. If the new grid reaches its limit, we will need to repartition our grid tree. The problem here is that every 3 seconds a lot of drivers will update their positions. So this cannot scale with this approach. To solve this, we can keep a hash table where the updates will be stored and instead of 3 seconds, we will update the grid tree every 15 seconds. For scalability, we should store the hash tree on multiple servers. Let's say we have a driver location server. As soon as the update call comes, this will broadcast the information to interested customers, and after every 50 seconds, it will update the grid tree. Now to broadcast this, we will register users as subscribers of our hash tree. So perhaps we can use a pub/sub model where the server will push the driver positions to subscribers' mobiles. We can have a dedicated notification service to do that. We can make this fault tolerant too by using a secondary server, and if that fails as well, we can periodically persist data in SSD storage since it provides fast I/O and recovery from the failure. Now for the matching part between a driver and rider, we can have a matching service. When a request comes in, our service will find the closest 10 drivers available and send them request. If we do this sequentially, the customer could be waiting for quite some time. So we will need to do this parallelly, and the driver who accepts the request first will be assigned. When the driver accepts, he will need instructions and directions to go pick up that user. So we can introduce a driver gateway which will be responsible for this, and we use it to maintain WebSockets since this will be a two-way communication. Since driver gateway will internally talk to matching service and location service, we can use gRPC for internal communications.